Hello everyone, for today's video lecture we're going to be talking about power in rigid body systems. So power is simply the rate at which you can perform work. So because conservation of energy relationship, so the rate at which you can perform work is also going to be equal to the rate at which your energy is changing in your system. So either one of those will work for power. Alright, so putting this all into equation, we arrive at the following. So power is dW dt, so the rate at which work is being done over time, or sometimes we'll do a time derivative with a dot, so W dot is also a valid way to write power. Alright, so if we look at the average power exerted over a set period of time, we simply divide work by time. So the average power is going to be the amount of work done divided by the time it's done in. And so working from the other direction, we can also, if we have the power, the average power in our system, multiply that by the time, we will find the amount of work done in our system. All right, so in translational systems for particles, what we talked about was work is a force times a distance over time, and then distance over time is then velocity. So if we have the force times the velocity of the object, that is also a valid measure of our power. At that particular instant, because velocity is going to be instantaneous. So in rotational systems, we can use moments and angular displacements instead of force and distance. So it's still work over time, but work is now going to be moment times the change in angle, delta theta, over time, or delta theta over t is going to be our angular velocity. So the moment times the angular velocity is another measure of power in a rotational system. All right, so the units of power, either translational or rotational, are going to be the same. So a watt is the metric unit of power. It's going to be 1 joule per second, or 1 Newton meter per second, force times distance over time. In the English system, it's going to be horsepower, which is 550 foot-pounds per second. So force times distance over time. This also works for rotational systems because our moment would be Newton meters or foot-pounds, and our delta theta is going to be in radians, which is unitless. So the units work out the same, rotational or translational. We've got watts or horsepower. All right, so power transmission is also another thing. So engineers are frequently going to need to work to transfer work or power from one location to another in a system. And the most common method for doing this is the rotational system. So if we have a combination of shafts, pulleys, gear trains, that is a power transmission system. So it's going from very old systems, where here we've got some pulleys transmitting power through a shaft, to even very new systems. So the transmission in your car is going to be transferring power from the engine to the wheels of your car. So if we measure the angular velocity and the torque in any kind of shaft along the way in our system, that's going to be giving us the power that's being transferred from the input to the output. And as we've dealt with before, for fixed axis rotation systems, the torques are going to vary from input to output. If we vary the size of the gears, vary the size of the pulleys, we can kind of change the torques that we have input to output. We change the angular velocities going with that. And the interesting thing with power is while belts, pulleys along the gear train are going to change those torques, those angular velocities, the overall power is going to remain the same at any one point. So belt and pulley systems, gear trains, they conserve power through the system, at least if we ignore friction. So there's always going to be some frictional losses, but if we minimize those frictional losses, power is going to stay constant through our system. All right, so rigid body systems in general, we could have rotation like we've been talking about, and that's pretty common. But we can also have systems where we have both rotation and translation happening at the same time. So if that happens, power is simply going to be the addition of the translational and rotational components of the power. So force times velocity, moment times angular velocity, or any of the other definitions we had for any of these systems. So we'll add the two pieces together to get the overall power. It is important for this, if you've got a system like this, the velocity in there refers to the velocity, the center of the mass of the body you're looking at, and the moment needs to be the moment about the center of mass of the body. So solving a power-related problem at its heart is still a work and energy problem. So we're therefore going to use a very similar process. Number one, you always want to set up your diagram, show the initial state, set up another diagram for some final state. If it's just a instantaneous system, you're going to have just one diagram. Identify any forces, any moments that are going to be doing work between the two states or at that instant. Identify the known or unknown velocities and angular velocities in each state, or just instantaneous velocity if that's the case. Identify any changes in height. So if you're moving something up, you're changing energy, potential energy, and then you're going to put together basically the work is equal to delta KE plus delta PE equation. So our work and energy equation, and just know that we're going to add in there our power. So we're going to have some sort of power relationship where power is the work divided by time. So we might put everything in terms of time. We might simply need to use that relationship. Each problem is going to be a little bit different, but just know that our time derivative of work is our power. All right, so once you have all those equations, put those together. Make sure you've got enough equations to solve for all the unknowns and solve those equations for unknown quantities. All right, so that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.